Okay, so we're going to deal with fluids in rigid body motion right here, as shown in this silly cartoon, where when we accelerate a body of liquid, it will generate a free surface that's influenced by that acceleration. So let's see, and that's related to the pressure gradient equations that we've seen previously here. All right, so let's say this liquid right here has this free surface that has that's at an angle right here, and that's because whatever this is, the camera and something is on. Let's say this jar and the camera are on some type of wagon, and someone's accelerating it, right? Not just with not a constant velocity, but having an acceleration that's going from left to right. So let's see. Let's switch over to our camera here. So we'll do a little bit of hand waving kind of stuff here, and this is section 3.7 in the book, and I think I'm pretty close to what they have inside here. So we accelerate. Now recall that we had this a general equation, right? So where we had the pressure gradient and minus the specific weight. So like there was something specific happening. This is a pressure gradient that's happening in all x, y, and z. But this one is only happening, let's say in the vertical direction is z here. So it's only happening when we have this. But now we actually have acceleration. Remember we were doing fluid statics where this acceleration was 0. For this equation right here, remember that we had an assumption of no shear, right? Which is another way of saying that it's inviscid. So this didn't include the effects of shear on this. If we break this thing apart and look at it, remember that we're going to have the partial derivative of the pressure in the x is going to be equal to the density times the acceleration in the x direction. We're going to have the partial derivative of the pressure in the y direction is equal to the density times the acceleration in the y direction. And then lastly, we're going to have the partial derivative of the pressure in the z direction is going to be equal to, and I move the gamma over to the other side right here, so it's no longer negative, plus the density and the acceleration in the z direction, right? So this is what that equation says up above, just made in more compact form. So let's treat the y for whatever reason as being the horizontal direction, and the z is the vertical. And let's say that we have some acceleration in that plane, in the yz plane. What's that going to do is going to generate lines of constant pressure, because that's what these are, right? These are describing how pressure is distributed in each of the directions right there. And we have this is our y and our z happening right there. And more importantly than we care about these other constant pressure lines, there is a constant pressure line which is the free surface of the liquid, right? The constant pressure would be atmospheric pressure. So we could describe the slope if we could just focus on dy dz, right? If we can get things in that form, dy dz, that's going to be the slope of this free surface. If we apply the chain rule to pressure, notably we will get, I need to squeeze some things in here, sorry about that, dp is equal to del p del y dy, right? That's just the chain rule. And same thing, d del p del z dz, right? Now, if you also, okay, so that's one of the ingredients. The other ingredient is what we've written up above, that we could say for also just looking at pressure as it relates, or maybe we could say that we're substituting in here that the dp is going to be negative rho acceleration in y direction dy and minus whoops, did I do that wrong? No, I'm good. Okay, I'm taking the density out here, taking the density out of the z direction, and we're going to go g plus az dz. So if we say, well, we're going to have a line of constant pressure, well, let's set this equal to 0, right? So that's going to be the free surface. the free surface of this equation and what we're left with, and we could rearrange it. We could have dz dy now, and we can get rid of the rows. So all we're left with is dz dy is equal to negative ay over g plus az. Right there. So this is the relation that we're looking at right here. And note that dz, the acceleration, did I say dz? I meant az, right? The acceleration in the z direction. This is often going to be 0. So that's the case like in the cartoon right here. He's only accelerating in the y direction. He's not accelerating in the z direction. So we just are able to find what that slope is going to be. So he has like acceleration in the y direction as shown right there. All right, we're 5 minutes into it. Okay, cool. So here's a simple example. I don't know how much more time this will take up, but there's an example right here. Let's say that we have this thing of gasoline. We say it was gasoline, yeah. But it's not gonna. It's gonna turn out it doesn't matter, right? Because the equation that we just got done using right over here was not dependent on the density, right? But we want to find out. Well, let's read it. The open rectangular container, right? So this right here doesn't have is open at the top. Is 2 meters wide and 1 meter, 1 meter wide and 2 meters long, right? So it's gonna be moving in that direction. And the tank has a height of 1.5 meters. But when you start out right there, the gasoline right here. So this is gasol. You just call it gasoline. That it's full to 1 meter, and we want to find how high or how fast, not fast, but how much. What's our maximum horizontal acceleration that we can have so that the gasoline will go bloop and start spilling out, right? So I redraw my little figure right here so I can kind of narrate this to myself. And here is the initial depth. And so as it's going to accelerate, right, it's going to form right here a line that's kind of like this right here. And we want to find out, right, we don't want any to spill out. So that's going to allow us to establish. So here's the acceleration. So here is 2 meters long, and this is 1.5 meters high. And so that would mean, like right here, this is what the other thing is going to be, right? But this is going to form a trapezoid, and we could even just kind of like know from kind of the conservation of mass, and conservation of density, or we could say for constant density, right? So constant density. Because we're treating this as incompressible, therefore the density doesn't change, therefore constant volume. And even more so, because we have a constant width to this thing right here, that means we're going to have a constant area. So this area right here has to equal that area right there. That's something that we can kind of like establish just from some logic in there. And therefore, this is going to be 0.5. right there, that level, right? Because this started out as 1 right here, so it went up. If it's at its maximum acceleration, this is where the level would be just before it tips over and drips out. So if it went up 0.5 meter here, it has to go 0.5 meter there. So the slope of this, and if we decide that this is going to be y and this is going to be z right there, then the slope is going to be dz dy, but the depth is getting less as we come down here, so it's actually going to have the slope of this part is going to be it's going to be 1 meter, right? I'll go 1 right here, but that's actually a negative 1 meter because it's going downwards as we go with increasing y. And then right here it's going to be 2 meters, right? So we have a negative 0.5 meters well, there's not meters, no units, right? It's meters per meter if you want, right? But that is the slope that we're looking at. Then if we set it equal to our equation that we just established over here, where we had negative AY over G plus AZ, right? Well, we have no AZ, so that's going to be just negative AY over, and we're dealing with metric, so 9.81 plus 0 is going to be equal to negative 0.5. So we've established that the maximum amount of acceleration that we could have to avoid slipping is going to be 1/2 9.81, which is 4.905 meters per second squared. So this is the max allowable. And truth is, you know, we would actually probably generally put a safety factor on top of that. We're not going to in this case right here, but just keep in mind that, you know, we could hit a bump, right? So if you're going to establish like, hey, you can't go over this acceleration, we'd probably want to establish that there's some kind of like margin there to protect ourselves from actually going over it. But if we were answering the question specifically, just what is the maximum, we wouldn't bother with the safety factor, but just keep that in mind. All right, so that's the end of video 3.